You've been on this flight, descending into London or San Francisco, and outside the window there's nothing. No horizon, no ground, no runway lights, just a solid wall of gray pressing flat against the glass. You can't see the wingtip. You start bracing, half expecting the pilots to pull up and try again. Then, thump. You're on the runway. A 300,000-pound aircraft just hit a 150-foot wide strip of concrete at 150 miles per hour, and nobody in the cockpit could see it. Most people assume the plane is using GPS. It's the most logical guess. GPS navigates your car to within a few feet. But standard GPS isn't precise enough to land a commercial aircraft. The vertical accuracy is off by meters, and if the satellite signal degrades, it can take several seconds to flag the error. At 150 miles per hour, a few seconds of bad data is hundreds of feet of blind flight. The system that actually lands the plane doesn't use satellites at all. It uses radio waves broadcast from the ground, a radar that argues with itself, and 3 computers that vote on whether to trust each other. Here's what a zero-visibility landing feels like before any of the engineering. The aircraft is descending through solid cloud. The cabin is quiet except for the engines, which keep making small adjustments, spooling up slightly, then easing back, spooling up, easing back, as if the plane is breathing. You feel the aircraft hunting gently left and right, correcting in ways you'd never notice on a clear day. The flaps extend fully, and the trailing edge of the wing drops away, exposing tracks and actuators, looking almost like it's coming apart. Then, somewhere below a few hundred feet, the gray outside the window gets brighter. Not clearer, brighter. High-intensity runway lights start bleeding through the fog. You see them for maybe 2 seconds before the wheels hit. The touchdown is firm, noticeably firmer than most landings. The nose pitches up slightly, then drops, and the main gear connects with a hard thud followed by immediate, aggressive deceleration. Auto brakes and thrust reversers firing almost simultaneously. If there's a crosswind, you feel something else just before the wheels connect. A sharp sideways lurch, as if someone kicked the tail of the aircraft. Then it's over. You're rolling down a runway you never saw. Every one of those sensations, the hunting, the engine breathing, the firm touchdown, the sideways kick, is a different system doing its job. None of them involve GPS. The system that aligns the aircraft with the runway is called the Instrument Landing System, ILS. And the first thing to understand about it is that the word beam doesn't describe what's actually happening. Most explanations say the ILS sends a radio beam into the sky, and the airplane rides it down like a rail. That's a reasonable image. It's also wrong. A radio antenna can't draw a line in the atmosphere. It emits an expanding cone of energy. You can't ride a cone. What the localizer actually does is transmit 2 overlapping signals simultaneously across the entire approach corridor from a row of antennas at the far end of the runway. Both signals carry 2 low-frequency tones, 90 Hz and 150 Hz. But in the second signal, the 150 Hz tone is deliberately inverted. Its peaks flipped to troughs, its troughs flipped to peaks. As both signals spread across the approach corridor, wave interference takes over. On one side of the runway centerline, the 90 Hz tones from both signals align and reinforce each other, while the inverted 150 Hz tones cancel out through destructive interference. On the other side, the reverse happens. The 150 Hz tones combine and the 90 Hz tones destroy each other. And exactly on the runway centerline, the inverted signal cancels itself out completely. The aircraft receives only the original unmodified transmission, where both tones are perfectly balanced. The receiver onboard measures which tone is louder. More 90 Hz means left of center. More 150 Hz means right. When the 2 tones are equal, when the difference is precisely 0, the aircraft is on the center line. The path the aircraft follows to the runway isn't a transmitted signal. It's the absence of one, a void in the radio spectrum where 2 waves deliberately destroy each other. A void doesn't sound like something you'd trust to guide 200 people to the ground. But wave cancellation is more precise than any beam a single antenna could produce. The null zone doesn't spread, doesn't scatter, doesn't fade with distance. But that precision cuts both ways. Because the center line is sculpted from radio interference, any large metal object near the antenna, a taxiing aircraft, a fuel truck crossing too close, can scatter the signals and bend the path in the sky. During low-visibility operations, airports push all ground traffic behind holding lines hundreds of feet farther from the runway than normal to keep the radio physics undisturbed. The glide slope uses the same principle rotated vertically, Same two tones, same phase cancellation, broadcast from a mast beside the touchdown zone, defining a 3-degree descent path. The autopilot chases 0 in 2 axes simultaneously, left, right, and up, down. Those gentle corrections you feel during the descent, the slight banking, the small pitch adjustments, that's the aircraft nudging itself back toward the point where both differences equal 0. If the ILS could guide the aircraft all the way to the pavement, the story would end here. It can't. The glide slope signal originates from a mast beside the runway, not from the pavement itself. As the aircraft descends, ground reflections corrupt the signal, and multipath interference makes it noisy. If the autopilot kept tracking it to the source, it would fly the aircraft into the dirt next to the runway rather than onto it. Below 200 feet, the vertical guidance degrades. Below 50 feet, it's too unreliable to use. So, at the exact moment the aircraft needs the most precise altitude information it will ever need, the final seconds before the wheels hit concrete, the primary navigation system goes dark. What takes over is a radar altimeter bolted to the belly of the aircraft. Not a pulse radar, the aircraft is too close to the ground for that. A pulse radar sends a burst of energy and times the echo. But at 20 feet above the runway, the echo returns in roughly 40 nanoseconds. Too fast to measure reliably for a system that needs to know height within inches. The altimeter uses something called FMCW, Frequency Modulated Continuous Wave. It transmits a continuous microwave signal straight down at the ground, but constantly sweeps the frequency up and down. The signal hits the concrete and bounces back. By the time the echo returns, the transmitter has already shifted to a slightly different frequency. The altimeter mixes the outgoing signal with the returning echo, and the difference between the two frequencies produces a low tone, a beat frequency that is directly, linearly proportional to the aircraft's height above the ground. Lower altitude, lower beat. The relationship is instantaneous. No satellite geometry errors, no atmospheric pressure drift, no processing lag. The aircraft knows its exact height above the concrete by listening to the pitch of its own radar arguing with its echo. Every other navigation system on the aircraft talks to something in the sky: satellites, radio beacons, waypoints. The radar altimeter talks to the concrete. At 50 feet above the runway, roughly the height of a 5-story building, the glide slope drops out entirely and the radar altimeter takes over. The localizer still holds the lateral center line, but from here down, every decision, the flare, the thrust reduction, the moment the wheels hit concrete, runs on one sensor measuring its own echo. That sounds like reasonable clearance. It isn't. At a descent rate of 700 feet per minute, 50 feet is about 4 seconds. 4 seconds to calculate the sink rate, pitch the nose up, pull the engines to idle, and in a crosswind, kick the rudder to align the wheels with the runway. At exactly 50 feet of radar altitude, the autopilot abandons the ILS glide slope entirely. It reads the aircraft's sink rate from the altimeter and commands the elevators to pitch the nose up, bleeding the descent from 700 feet per minute down to roughly 2 feet per second at touchdown, the descent speed of a slow elevator. At about 30 feet, the autothrottle pulls the thrust levers to idle. That moment in the cabin when the engines suddenly go quiet right before landing, that's not the pilot easing off the power. That's the radar altimeter crossing a threshold and the system commanding the engines to stop flying. If there's a crosswind, the aircraft has been approaching at an angle, nose pointed into the wind to hold a straight ground track over the localizer centerline. Landing sideways would shatter the gear. So at roughly 5 feet above the concrete, the autopilot kicks the rudder hard, swinging the nose into alignment with the runway in a fraction of a second. That sharp sideways lurch you feel just before the thud is the system solving a geometry problem at 150 miles per hour with 5 feet of clearance. The touchdown is firm because it's programmed to be. The autopilot isn't greasing the landing for comfort. It's putting the aircraft into a specific touchdown zone with positive contact, so the weight transfers to the wheels and the auto brakes can fire immediately. None of this works if a single computer is running the landing. One processor fails at 40 feet and 200 people are riding an unguided object into fog. For the lowest visibility landings, Category 3, which only certain aircraft and airports are equipped for, the aircraft flies on 3 independent autopilot computers simultaneously. Each receives the same ILS data and the same radar altimeter readings. Each calculates its own control inputs. Each compares its answer to the other two. If one disagrees, computes a slightly different elevator command, or reads a different altitude, The other two vote it out. They isolate the faulty computer and continue the landing on the remaining pair. The pilots get a notification that redundancy has decreased. The wheels touch down without a deviation in the flight path. For the system to be certified, engineers must mathematically prove that the odds of catastrophic failure are less than 1 in a billion flight hours. The landing doesn't depend on the computers working. It depends on them failing correctly. The story of how humans first solved the problem of landing blind starts well before any of this technology existed, with a canvas hood, 3 crude instruments, and a technique that would be illegal in every country on Earth today. If you want the next one of these to show up automatically, subscribing takes 1 second. On September 24, 1929, Army Lieutenant Jimmy Doolittle climbed into the rear cockpit of a modified biplane at Mitchell Field, New York. A canvas hood was snapped shut over the cockpit, blocking all outside vision. A safety pilot sat in front with his hands raised to prove he wasn't touching the controls. Doolittle had 3 instruments: a gyroscopic artificial horizon, a barometric altimeter, and a set of vibrating metal reeds on his dashboard. A ground station transmitted overlapping radio signals. If he drifted left, the left reed vibrated. Right, the right reed. He steered to keep both reeds shaking equally. His technique for the actual touchdown was blunt. He pointed the aircraft at the ground at 60 miles per hour and let the landing gear absorb the impact. The first blind landing in human history was, in the most literal sense, a controlled crash. Radio signals for the centerline, a crude sensor for altitude, and the landing gear absorbing what came next. The precision has improved by orders of magnitude since 1929. The physics haven't changed. It took 36 more years to get a computer to do what Doolittle did with his hands. In 1965, a British European Airways Trident completed the first fully automatic landing at London Heathrow. The system used 3 independent autopilots because early transistors failed too often to trust just one. That triplex architecture became the template for every Autoland system flying today. On February 25, 2009, Turkish Airlines Flight 1951 was descending toward Amsterdam's Schiphol Airport. At 2,000 feet, the captain's left radio altimeter, the same type of FMCW sensor that triggers the flare, suffered a hardware failure. It began reporting an altitude of -8 feet. The aircraft was at 2,000 feet. The altimeter said it was below the ground. The autothrottle, designed to pull the engines to idle when the radar reads landing altitude, did exactly what it was programmed to do. It retarded the thrust levers. The engines went quiet. The aircraft, still 2,000 feet in the air, began bleeding speed. For nearly 100 seconds, the throttles stayed at idle while the pilots focused on intercepting the glide slope. By the time the stick shaker fired, the stall warning physically shaking the control column at 490 feet above the ground, the aircraft had slowed to 40 knots below its safe speed. The captain slammed the throttles forward, but jet engines don't produce instant thrust. They need seconds to spool up. The aircraft didn't have seconds. 9 people died. Every component in the chain had worked exactly as designed. A single sensor error cascaded through the interconnected system, radar altimeter to auto-throttle to airspeed to aerodynamic stall, and flew a perfectly functional aircraft into the ground. The training protocols that now require pilots to actively monitor airspeed during automated approaches, regardless of what the computers are doing, trace directly back to that flight. The next time you're descending through fog and the window shows nothing but gray, here's what's happening around you. 2 radio signals are destroying each other in the air ahead, and the aircraft is chasing the void where they cancel out. A radar on the belly is bouncing microwaves off the concrete, measuring height by the pitch of its own echo. 3 computers are comparing answers, ready to vote one out the moment it disagrees. And at 50 feet, 4 seconds from the ground, the autopilot abandons the radio signals entirely and commits to landing on radar and physics alone. One more thing. The technology to land in absolute zero visibility exists. Category 3C. No decision height, no minimum visual range whatsoever. It's been engineered and tested. No airport in the world is certified to use it. Not because the aircraft can't land blind. Because after it lands, the pilots can't see well enough to find the taxiway to the terminal. The plane can land itself in zero visibility. It just can't park. What's something you've noticed during a flight that you've never been able to explain? Put it in the comments.